Section 10.3 is on page 703, talks about representing graphs and graph isomorphism. Well, isomorphic graphs are very important in programming and applications. This is straight cut from the book. There are many useful ways to represent graphs, as we will see throughout this chapter. In working with a graph, it is helpful to be able to choose its most convenient representation. In this section, we'll show how to represent a graph in several different ways. Sometimes two graphs have exactly the same form, in the sense there is a one-to-one correspondence between the vertex sets that preserve edges. So they might look slightly different, but you actually could look totally different. But you're pretty much worried about, can I reset this? Can I have a one-to-one correspondence between the vertices and the edges? In such a case, we say that the two graphs are isomorphic. Determining whether two graphs are isomorphic is an important problem of graph theory that we will study in this section. One way to represent a graph without multiple edges is to list all the edges of this graph. Another way to represent a graph with no multiple edges is to use adjacent lists. I'm going to do an example on all of those, which specify the vertices that are adjacent to each vertex of the graph. Suppose that G consists of vertices and edges is a simple graph where there are n vertices. Suppose that the vertex of G are listed. These are all the vertices of G. The adjacency matrix A sub G of G with respect to this listing of the vertices is an n by an n. It's a square matrix, zeros and ones, and the traditional. I'm going to do an example on that. We need to get these matrices in because that's really going to be very helpful for us in the long run. One definition: a simple graph G1 where you take vertex 1 with edge 1 and G2 with V2, E2 are isomorphic if there exists a one-to-one correspondence and onto function from V1 to V2 with the property that A and B are adjacent to G1 if and only if f of A, f of B are adjacent to G2. This is mathematical terms. Not an issue. I'll show you that with an example. It's a lot easier than you think for all AB belonging to V1. So it's not random. It has to be very specific. When I look at the characteristics of each of those one-to-one correspondence, it should be identical. Such a function f is called an isomorphism. Two simple graphs that are not isomorphic are called non-isomorphic. So let's start with the first example. This is on page 710. So use an adjacency list to represent the given graph. Again, I didn't give you the definition for this because it's common sense, it's long. So when I say, hey, let's talk about a vertex, put them in order. I see vertex A, vertex B, vertex C, D, and E. And I want to talk about adjacent vertices. The adjacent vertices to A, well, obviously B and D. To B, that is A, D, and E. To C, only two, D and E. To D, A, B, and C. And to E, only two, B and C. Done deal. That's it. And here, if I label the vertices of what I have, adjacent vertices, I have A, B, C, D, and E. For A, I notice from A, I have B and D. these are directed. You got to be cautious with those. And if I look at B, from B there is A, there is C, there is E, and there is D. Oh, D. Should put them in order. From C, there is B, and there is C. This one doesn't count because that's coming to it and I going out of it. So directed, you got to be a bit more careful. Where can you go from C? You can only go to B or to C itself. If I look at D, there is A. B doesn't count because you're coming to it, not going away from it. And there's E. That's it. And from E, you could go from E, you can't, that doesn't count, that doesn't count. You could go from B to C, and E, from E to C, and from E to itself. Now let's talk about this matrix business. Well, this matrix business you're gonna like. So 1, 2, 3, 4, 5. There, 5 by 5. So it's kind of, you don't have to write them. A, B, C, D, E. A, B, C, D, E. So let's see. If I look at A doesn't have a loop to itself. So I'm reading this way. A to B, there is a connection. A to C, there's no connection. There's only A to B and A to D. The rest, no connection there. From B, if I start at B now I'm starting here. There is no loop to itself. So a loop to itself, that will be a 1 since there's no loop. And again, I'll show you an example coming up on number 8. This is directed and non-directed. How about, I'm sorry, I messed up. That's not what I meant. B to B, there is no loop to itself. But B to A, there is one. It's right there. And B runs to D and E. To D and E, but not to C. You notice there's no connection between those two. Now I go to C. C is right there. If I look at C, C can connect to D and E only. C can connect to D and E only. The rest, it can't connect to any of them. D can connect to A, B, C. A, B, C, and it can't connect to anything else. And if I go for E can only connect to B or C. The rest, it can't connect to. And that's how we do those. And again, a matrix is extremely important for applications. In example 8, we're doing the same. We still have a 5 by 5. Okay. So again, A, B, C, D, E, A, B. You don't have to write those on the side, but it helps to write them. So let's start with A. This is directed now. You got to be a bit careful. A runs to B. There's no A to itself. A runs to D. That's it. The rest are all zeros. If I go for B, B runs to A. B doesn't run to itself. B runs to C. B runs to D. And B runs to E. C runs to itself. That's CC. So C runs to A. No, it doesn't. C runs to B. Yes. C cannot run to either of those. And if I go for D, D runs to A, yes. D runs to B, no, it doesn't. B runs to C, it can't reach it. B only can run to E. And E cannot run to A. Actually, this doesn't count. This doesn't, the only thing it could run to from B, you could run from B to C or itself. Okay. Now, can we go backwards? Draw a graph with the given adjacent matrices. Well, on number 10, we have A, B, C, A, B, C, and we notice A runs to B, B runs to A, so there's a connection between A and B. There's also a connection between B and C and B. So there's A, there's B, they keep them as lower cases. So A to B, here we go. B to C, here we go. So A to B, B to A is the same one. B to C and C to B. Now, of course, now that you know what it looks like, you could even do them this way if you want. It doesn't really matter. So I could say those two are isomorphic because B has two connections. A has only one and C has only one. And we'll talk about isomorphic when we get there. How about this graph? A, B, C, D. So there's A, there is B, there is C, and there is D. We go in order. From A to itself, there's a loop. From A to B, there is from A to C, there is a connection. There we go. A is done. There's no from A to B. From B, so this is A, B, C, D. From B, there's no connection to A. There's no connection to itself. There's connection to C. And that's it. B only has one connection. C has a connection to itself, a loop. C has a connection to A. Oh, I messed up. This should have been the first, and this should have been the loop. This is the loop, C to C, and that's it. D has a connection to A, a connection to B, a connection to C, but no loop to itself. And that's pretty much it. Represent the graph using adjacency matrices. Okay, how does this work? There's only 4 of them. So if I run from A, I could run from A to itself, there's none. Actually, B to B, there's none. C to C, there's none. And D to D, there's none. Get those out of the way. Right? They can't connect to themselves. There's no loop on any of those. Let's talk about A. A happened to have 1, 2, 3 to B, and 1 to D, none to C. B happens to have 3 to A, 1 to C, and that's about it. C has 3 to D, C has 3 to D, 1 to B, none to A. And D has 3 to C, 1 to A, and that's it. Draw an undirected graph represented by the given adjacency matrix. All right, how do we do that? We have ABC, A, B, and C. So A, B, C, A, B, C. It seems A to A, there's a loop. A to C, there are 3 connections. A to B, there are 3 connections. 1, 2, 3. A to C, there are 2 connections. 1, 2. Now, I go to B. B to A, there are 3, it's already there. B to B, there's no loop to itself. B to C, there are 4. B to C, there are 4. Oops. 1, 2, 3, 4. And if I go from C to A, there are 2, they're right there. C to B, there are 4, and C to itself, there's none. There it is, you're done. Find the adjacency matrix of the given directed multi-graph with respect to the vertices listed in alphabetical order. Okay, we have 4 of them. Directed, remember the arrow going, so I'll show you again in case we're missing it. So from A to A, there is a loop. From A to B, there is 1 because the direction runs this way. From A to C, there is 1. And from A to D, there is 1. Let's go from B. B to itself, there's a loop. B to A, that doesn't count. I said the right thing and I wrote the wrong thing. B to A, there is none. B to itself, there's a loop. C to itself, there's a loop. D to itself, there's a loop. So get those out of the way. That's the loop. That's a diagonal. That's what this is called. The diagonal is always the loop because you're going to itself. Well, let's see. How about B to C? B to C, I don't see any. And how about B to D? I see it right there, that direction. If I go for C, I already got the loop. C to A, it's right there. C to B, there's none. I can't see a connection between those two. And C to D, you see the direction is running this way, that doesn't count. And if I go from D to A, right there. D to B, right there. D to C, right there. And D to itself, and there it is. Almost done. Draw the graph represented by the given adjacent. Okay, now we want to do 3 of those. A, B, C. A to itself. And A to C. B, not to itself, not to A, only to C. And actually, yeah, you could put them directed or you could put them undirected. It doesn't matter. And normally, if there's a loop, you direct them. Yeah, A to C. Okay, there we go. B to C. And C runs to A. Let me see, draw the graph represented by the given adjacency matrix. Yeah, if there are only 3, you only draw them. You only draw simple. So we said A to A. We run A to B. Only 3. But there's no A to B. It's A to C. B to C. And C runs to A, C runs to B, and C runs to itself. There. So if there's only 3, you draw a simple graph. You could write directed if you want. You're not going to lose anything, but that's what it is. Now let's talk about this isomorphic stuff. If I look at 38 to 48, determine whether the given pair of graph is isomorphic. Exhibit an isomorphism or provide a rigorous argument that none exist. For additional exercises of this kind, you could look at these examples, not an issue. So let's see. I notice there's one edge. I'm thinking if I map those two, that looks very good. That looks like this because it has 2. U3 looks like V4 because this has 2 and this has 2 and one common, and there it is. And if I look at V, looks like that, and it appears this has only 1 and there it is. So you're going to have to say that. If you say this is isomorphic, you're going to have to tell me that I want so you're kind of mapping the vertices with the same characteristics. They don't have to go in order, by the way, and you'll see that really quick. Notice this is U3, this is V4. And f of U4 is really the same as V5. And f of U5 is really V3. So this to this. U2 is really matching V4. Oh, wait, what? Oh, I'm sorry. U2 is mapped. I clicked the wrong button, I'm sorry. U2 is mapping V2. Okay, here. U3 is really mapping V4. U4 is looking like V5. Again, it has to because there's a connection between those. So don't think, oh, we could just go from A to A, B to B, and that's not how it works. You just got to be cautious when you do this. Here, could this be isomorphic? If they are, you're going to tell me how this works. Well, notice, look for the 2, 3, 3, 2. Look for the most and the least. 1, 2, 3, 4. This is 2, this is 3, this is 3, this is 3, and this is 3. This is not isomorphic. Why is that? Well, the left, let me go this way, it's better. The degree of V2 is 4. No match on the left. Yeah, I like it to look nice. I wasn't sure how much spacing I need, so I left it without those. Now I put them from the beginning. Let's adjust really quick. All right. And last couple. So when I glance at this, I'm trying to figure out, would this work? Let me see. I'm looking at 42. So 2, 1, 2, 3, 4, 1, 2, 3. So here, I could think of it this way. I have 3, 2, 4. I'm going in this direction. 4, 4. That's it. And here, I notice I have 3 going in this direction. 4, 2, 4, and 3. Do they match? Let me double check. 1, 2. Okay, we got that. We got 1, 3. We got 1, 3. We got 4s, 2 4s. We got 3, 1, 2, 3, and we got 4. Let me see. 1, 2, 3, 1, 2, 1, 2, 3, 4, 1, 2, 3. So yes, they do match. And the reason I'm saying this, I worked around my notes. I'm like, okay, yes, it is isomorphic. And how does that work? I'm going to have to match the 3's with the 3's and the 4's, but I want to make sure that they connect to the same thing. So f of u1, so pretty much I'm going to say this is very close to this one. That's good. We could do that. That's... Then I'm going to look at u2, go in this order. u2, 1, 2, 3, 4. So since u1 connect to u2, I want v1 to connect to something with 4. That looks like v3. So now I'm saying this is equivalent to that. And I would run from, there's u2 connecting to u3. So now I'm looking at, I'm going to connect v3 to v2. So that works. F of u3 equal v2. And in this case, we're saying this and that are the same. And you'll notice the same connections, two of them. Well, one of them runs to v2 and the other one runs to what? To u4. So v2 runs to u4. u4 is going to take the place. The only other connection we have is v5. So again, if I look at the 3 connections, they have to match between those two when I'm done. So that's how you do it. And the last I have, u4 connects to u5. And here, v5 connects to v4 in that order. So they share the same characteristics. Make sure that they share the same degree and they connect to the same sort of work. It's really not as complex. This is, you'll pick this up pretty quickly. How about this one? Well, let's see. 3, 3, 2, 2, 2. Okay, 3's and 2's. 2, they have to match identically, but let's see. 3, 1, 2, 3, 4. There we go. Degree of V6 is 4. None on the left match. That's good enough. And how about this one? So if I look at the most, 1, 2, 3, 4, 1, 2, 3, 4. Very good. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, this has 4, this has 4. But we have an issue. These are adjacent. These are not adjacent. It's very hard to do. That's not going to match. So we could say left degree of u2 equal degree of u3, which is 4, and they are adjacent. But here there's no way of making this connection. On the right, v2 and v4 are 4, but they're not adjacent. So this is not isomorphic. And that's pretty much it for this section.